Editing Sam back once again, fixing a few things after I decided to change how I was going to talk about these topics. Episode 4 is now about Riemann sums and their graphical significance, the relationship with a Riemann sum for a function, and the graph of a function. Our new objectives are we're going to be describing the relationship between the Riemann sum formula and the graph, and we're also going to be using the graph of a function as a quick and easy way to check to see if our Riemann sum calculations make sense or if the value that we calculated is totally outrageous and absurd, and if we made a mistake. I want to talk a little bit about the graphical meaning of these Riemann sums, relating the Riemann sum that we've just calculated to the graphical representation of a function. So here I've just sort of stolen this picture off of Wikipedia. Here's our Riemann sum formula, and here graphed in this picture is just a random function, random polynomial f of x. Now down here on the x-axis is the interval from a to b. And this interval has been split into pieces, and the distance between those pieces on that interval is what we call delta x. So notice that in this picture, delta x is showing up as a width. Now notice as well, remember in our review bite from yesterday, that when you plug a value into a function, the graphical significance of that output is that that output corresponds to a height on that graph. So in particular, if you choose a random x value out of one of your chunks on this x-axis, and you plug that x value into the function, that output value is corresponding to a height on this graph. So now you have heights and you have widths. And if you multiply together a height and a width, as we have a product in this Riemann sum, height times width gives you area. Height times width gives you the area of a rectangle. And if I add together all of those areas, total area of all these rectangles that are sort of attached to the graph of f of x, and notice that that total area of all these rectangles is at least a decent approximation, at least a decent estimate for the area underneath the graph of the function. Let me show you another picture to make that idea a little clearer. Someone graphs a generic function f of x on an interval from x equals a to x equals b. The area underneath that graph is given by this sort of smooth area, is given by what is here drawn in orange. The Riemann sum calculates the total area, a bunch of different rectangles that are sort of attached to the graph of f of x at either the upper left corner or the upper right corner, depending on whether you take a left Riemann sum or a right Riemann sum. So the total area of these rectangles is a decent approximation to the area underneath the graph of f of x. Let's summarize that. In the Riemann sum calculation, f of xi graphically represents the height of points on the graph of your function. Delta x represents widths between the points on the graph of your function. If I take the product of this height and this width, I get an area of a rectangle, which is attached to the graph of the function. And if I add together all of those areas using a sum, then I get a total combined area of all of those rectangles together. And this total combined area represents an estimate, an approximation for the area that's underneath the graph of f of x. The Riemann sum is an estimate for the area that's underneath the graph of your function. The Riemann sum is an estimate for the area that's underneath the graph of your function. Now, with this picture, notice that this assumes that the function f is always positive. This function f is always above the x-axis, and in that regard it makes sense to talk about the space underneath the graph, between the graph and the x-axis. But we also know that there are many functions out there where the function dips below the x-axis. And so the question is, if your function ever dips below the x-axis, if the function is ever negative, what is the Riemann sum indicating, signifying in that case? Well, in that case, you can still think about the Riemann sum as capturing an area. However, if you're dealing with a point on the graph where your function outputs a negative value, if f with this x plugged in is negative, then when I apply that negative value to this product of height times width, then that negative height times this positive width is going to give you a negative area. So this is an area with a sign attached. The area of the rectangle is basically being assigned a negative value to capture the fact that this particular rectangle would be below the x-axis instead of above the x-axis. So this is something that you may have seen in physics before when you talk, for example, about negative position or negative velocity. That negative sign just communicates some additional information. Negative velocity, for example, tells you how fast you're going, but it also tells you that you're going backward. In a situation like this, we also have what we could think of as a negative area. The negative sign tells you that the area is located below the x-axis. If you're dealing with an area that's below the x-axis, the area is ascribed that minus sign to communicate that extra little bit of information. Negative areas below the x-axis. Now, if you have some negative areas that are below the x-axis, and you have some positive areas that are above the x-axis, then when you do the summation in the Riemann sum, to add all of these negative and positive areas together, some of them will cancel out. The negative areas will cancel out portions of the positive areas. And when you allow negative areas and positive areas to cancel each other out like that, the sum total is what we call the net area. For the net area between the graph and x-axis. So to emphasize, the difference between net area and area is that net area, it considers areas to be positive if they are located above the x-axis. It considers areas to be negative if they are below the x-axis. And so if you have a graph, if you have a function that dips below the x-axis, then the Riemann sum is estimating that net area. If you have a function that dips underneath the x-axis, the Riemann sum is estimating that net area, which counts areas above the x-axis as positive and areas below the x-axis as negative. Now, if you keep this in mind, you can, get a decent approximation for the value of a Riemann sum just by looking at the picture, by looking at the graph of a function. So let's exercise that idea here. So someone gives me the function absolute value of x minus 3, then quantity take away 1 unit. So that's given here, this V-shaped function here in this picture. And someone says, okay, somebody says calculate a Riemann sum for this function on the interval from 1 to 4. If you did that, approximately what kind of value would you expect to see as a result of the Riemann sum? Now, to answer this question quickly, I'm going to remind myself that the Riemann sum and the net area are approximately the same. So if I can use the picture to get a rough idea of what the net area would be, then I can use that as an approximation for what the Riemann sum should be. Now, let me explain to you why we're doing this kind of problem. We're doing this kind of problem for a couple of different reasons, but the first reason that I want to bring to your attention is that one of the domains of knowledge, the computation domain of knowledge, involves you being able to check the result of your calculation to see if it makes some kind of sense. And that's what this exercise is about. We are using the graph as a tool that can be applied to see if the result of our Riemann sum calculation makes sense. This is an exercise toward that skill. So let's look at the picture and see if we can estimate the net area between this function and the x-axis over the interval from 1 to 4. So here is x equals 1, and here is x equals 4. And if I look at x values between 1 and 2, on that region, the function is above the x-axis. The function is positive on this region. So this portion of the area would be given a positive sign. This would be a positive area because it is above the x-axis. And as a matter of fact, because this particular region is triangle shaped, we can use geometry to find its area exactly. The area of this triangle would be 1/2 the base of the triangle times the height of the triangle, 1/2 1 times 1, which would be 1/2 unit. And again, this would be a positive half. Now, if I move a little bit further along that interval, and I look at the region from x equals 2 to x equals 3, then the region between the function and the x-axis would be this one down here. And on this region, the area would be assigned a negative value because this particular region has our function below the x-axis, below the x-axis. Now, once again, we get a triangle shape. We can use a geometric formula to find the area of this region. 1/2 the base, which is 2 units, times the height, which is 1 unit. However, we would give this area a negative sign to capture the fact that this particular area is located below the x-axis. So this region would be called having an area of -1, an area of 1 unit located below the x-axis. Now, if I want to find the net area, all I have to do is combine this positive area and this negative area and allow those two answers to cancel each other out. The net area is a combination of the positive area with its positive sign and the negative area with its negative sign, all in total, the net area is around 1/2 units, negative. Negative area of 1/2 to capture the fact that this graph is mostly below the x-axis between x equals 1 and x equals 4. So what this means is if I were going to calculate a Riemann sum for this function over this interval, I had better be getting answers that are somewhere in the vicinity of negative 1/2. If I got an answer of positive 30, if I got an answer of negative 100, I would be pretty suspicious about that result. But if I got an answer of negative 0.3, if I got an answer of negative 0.8, now that seems a little bit more plausible. That seems more likely to be correct. You understand? So this gives us a way to check to see if our answer makes sense or if our answer is crazy. Let's demonstrate that idea in part B of this same exercise. We are asked to actually calculate a Riemann sum for this function over this interval from 1 to 4. And they say please use a delta x of 0.5 rather, and confirm that the result that you get is close to your answer in part A. So just as we did yesterday, in order to answer this question, I'm going to go ahead and set up a table of data. First row are my x values, second row are my y values, and I'm going to start with the first x value for my interval, which is 1 unit. Now the distance between this first x value and the next x value, I'm told, should be delta x equals 0.5. So going up 0.5 units brings me to 1.5, then another 0.5 units brings me to 2, then 2.5, then 3, 3.5, and 4, and I'm going to stop there. I'm going to stop there because that's the end of my interval, okay? Now that I have written down my x values, I'm going to go ahead and write down my corresponding y values. And each of these y values I am going to obtain by plugging this x into the formula that I was given at the start of the problem. Alternatively, you could also use the graph to answer this question and fill out this table. For example, if I wanted to know what y value was associated with x equals 1 by this function, then one option would be to plug 1 into my formula. Absolute value of negative 2 is 2. Take away 1 from that, result 1. So that would be one way to plug in this value. Perhaps even easier would be to use the graph. If I wanted to know, for example, what y value was associated with x equals 2, I could go to the graph, I could look for a horizontal position of 2, that's right here, and I could see that the corresponding height of that point is located here at 0. So right away I know that y value would have to be 0. 3, the height of that point is -1. Plug that in easily. 4, the height of that point is 0. I can plug that in easily. 1.5 looks like 0.5. 2.5 looks like negative 0.5. 3.5 looks like negative 0.5 again. So using either the formula or using the graph, we have now filled in the blanks in this table. Do you remember what our next step is toward using a Riemann sum to do this calculation? Our next step is to make a decision. The decision that we have to make at this point is about what we are going to choose for our x value out of each sort of piece or chunk of this interval. And the typical choices are to either choose the left x value or the right x value on each chunk, which will give you what we call either a left Riemann sum or a right Riemann sum. I am kind of fond of the left Riemann sum, so I'm just going to go ahead and do that. So if I, because of my personal tastes, am choosing to do a left Riemann sum, then on the first chunk, I'm going to choose this left x value. On the second chunk, I'm going to choose this left x value. On the third chunk, I'm going to choose this left x value. On the fourth chunk, the left x value, and then the left x value, and then the left x value. And if I choose the left x on each of these pieces, then I'm correspondingly choosing the left output. So the left output of 1, the left output of 0.5, the left output of 0, the left output of negative 0.5, the left output of -1, the left output of negative 1/2 again, and then I'm going to stop because negative 1/2 is the left y value on this final chunk here. Now remembering again, now that we have identified the x values and the corresponding y values that we are going to choose from each chunk, once we have chosen those values, the next thing that we do is multiply those values by delta x, going from heights of rectangles to areas of rectangles with this product. Now we are told that the width of each rectangle is 0.5. So what I'm going to do is I'm going to take our y value 1, multiply it by 0.5. I'm going to take our 0.5, multiply it by 0.5. The next y value is 0. The next y value is negative 1/2. The next y value is negative 1. The next y value is negative 0.5. And then I'm going to add together all of these areas of rectangles attached to my function. And let's go ahead and add up these values, giving me negative 0.25. That would be the value that is estimated from a left Riemann sum. And notice that this value is not that different from the net area that we estimated in part 1 via the picture alone. And that's the way it should be. The Riemann sum that you calculate, the value of that Riemann sum, should always be close to the net area, because the Riemann sum is just an estimate for the net area between the function and the x-axis. Okay? Now you can also do a calculation using a right Riemann sum, of course, and the right Riemann sum is going to give you a slightly different value, but it's still going to be close to this net area of negative 1/2. Let me quickly write up what the right Riemann sum would become. And remember that the right Riemann sum, the only difference is that it uses the right-hand x on each little piece, each little chunk, instead of using the left-hand x. And as a result, we'll be using this right y value on each little chunk and each little piece instead of the left value. So let me go ahead and calculate that, write that up. Okay, and here's the value that would be gotten by the right Riemann sum. The right Riemann sum gives us a value of negative 0.75. And again, 0.75 is a slightly different estimate, but it's still pretty close to the net area that we found in part A. And that is what we need, that is what we want. The Riemann sum, whether it be a left Riemann sum or a right Riemann sum, should always be outputting a value that is close to the net area, because the Riemann sum is an estimate for the net area. Takeaway: if the Riemann sum that results from your calculation is super different from the net area that you're seeing out of the graph, that's a huge red flag, and that indicates that probably you've done something terribly wrong in your calculations. So this is a way, by looking at the graph of the function, to check and see if your calculation makes sense, if it's probably kind of sort of correct, or if it's absolutely busted. Now in this exercise, I'm asking exactly the same question that we asked in part A of the previous exercise. Here is a function. It is graphed below. Based on the graph, approximately what value would you expect to see if you are asked to calculate a Riemann sum for this function over the interval from 1 to 4. The major difference between this exercise and the one that we had in the previous problem is that in the previous problem, the graph was an absolute value graph and was composed of these straight lines forming these triangular regions. And so that made it really easy to find the area exactly using geometric formulas. But in this example, by contrast, the graph is curved, and the regions that are created by the graph are not, they're not these nice geometric shapes that we have area formulas for. But again, we're going to use the fact that this question is just asking us to estimate things, just asking for approximate answers. Roughly speaking, what kind of value would you expect to see? Roughly speaking, what is the net area? And to answer that kind of question, I'm just going to eyeball this picture, and I'm going to use a rough eyeball of this picture to estimate the net area. So here is the portion of the interval where the function is below the x-axis, here between 2 and 4, and here is the portion of the interval where we are above the x-axis between 1 and 2. Now, each of these squares in the picture is 1 unit wide by 1 unit tall. So the area of a single square in the picture is 1 unit. So I'm going to estimate the net area essentially by just counting squares. For example, look at this positive portion here on the left side. If I wanted to estimate the area, then I would say, okay, this portion down here is a little bit less than 1 full square. If I combine that with this portion up here, this little triangular looking bit, then this little piece combined with this little piece probably together are making up, roughly speaking, 1 full square, 1 full unit of area. And then this piece in the middle looks like it's roughly speaking about half a square or a little bit less than half a square. So just by counting squares, I would estimate this area to be maybe somewhere around like 1.4 or something like that. Down here in this red portion, I could do a similar thing. I could say, okay, this looks like a little bit more than half a square. So a little bit more than half a square, maybe 0.6 units of area on this half, maybe around 0.6 units of area on this other half. So if I put them together, I would estimate an area of about 2 lots of 0.6, around 1.2 maybe. And I would give this one a negative sign because this is below the x-axis. This area is below the x-axis. So just for an estimate of the net area, I would combine the positive portion with the negative portion, add those together. I would say my net area here is really quite small, maybe a little bit above 0, maybe somewhere in the ballpark of 0.2. That would be my estimate for the net area. And so that would be my estimate for the value of a Riemann sum for this function. If I was getting a Riemann sum for this function of, say, like 22 units, I would know that that's crazy. Something's definitely gone wrong. There is a problem in that calculation. Because 22 units is way too big based on our estimate of the Riemann sum's value, based on our estimate of the net area. So net area. Net area, you can eyeball net area off of a graph just by basically counting squares and little portions of squares. And that's going to give you an estimate to tell you reasonable values of what your Riemann sum should equal. All right, that concludes episode 4. In episode 4, we looked at the relationship between the Riemann sum formula and the graph of a function. And by analyzing the different pieces of the Riemann sum formula, we noticed that the Riemann sum formula was connected to areas where the delta x was the width and the f of xi star was the height. The product of the height and width gave us areas of rectangles. Those areas were positive if the function was above the x-axis. Those areas were negative if that function was below the x-axis. And so when we total all those areas together in the Riemann sum, what we get is what we call net area, where those positive areas and those negative areas are able to cancel each other out in parts. So by looking at the graph, we can get a very rough, quick estimate of what the net area should be. And then when we have an estimate of what the net area should be, we have an idea of what our Riemann sum calculations should work out to be. So we have an idea of what kind of answers are reasonable and what kind of answers are totally unreasonable, to help us to know when a mistake might have been made.